Hello everyone, today I'm going to present about one of my recent works in the field of magnetic resonance imaging. In short, this work is about non-Cartesian MRI pulse sequence design. Before we dive into the math, let's quickly recall some background knowledge of MRI. In MRI, a common task is to acquire sufficient data to cover space. Without loss of generality, let's assume we are performing 2D imaging, and thus we have to acquire data to fill this 2D space. Hereafter, let's call it K-space. In conventional Cartesian MRI, this space is covered by multiple parallel lines, while in the non-Cartesian MRI, this is done by multiple curves, such as spiral curves, which can save much time by acquiring more data per acquisition. So here is the acquiring position in the K-space denoted by the gradient vector at the time. So to perform the non-Cartesian acquisition, we have to code the pulse sequence to control the gradient vector parameterized by time, which can drive the K-space sample along the desired curve. However, since gradient amplitude is essentially produced by the current in the gradient coil, the current by itself has an upper bound, and so does its slew rate. This becomes two hardware constraints in the gradient design problem. So the problem we want to solve is to design a gradient waveform to drive the K-space sample along the desired curve while respecting the hardware constraints. In early years, there are some people working on the closed-form solution of the problem for some specific type of the curve, such as spiral curve. Here I show a high-level outline of this kind of methods, but today we want to talk whether there is a general method which is suitable for any type of the curve, regardless of the mass type of the curve. Before we introduce the gradient design problem, let's look into another classic problem in kinetic science. Assuming there is a car running on an arbitrary path, the velocity and the acceleration of the car have upper bounds. We want to solve for a plan of the car velocity with respect to location. We also expect the transversal time to be minimum possible. This problem has been extensively studied. So Dr. Lustig proposed to transplant this method to gradient design because of the analogous relation between these two problems. And his method has been widely used. Let's call it optimal control method. Thanks to Lustig's source code, I successfully reproduced his method. However, we have found some limitations. The first one is about slew rate control. We all know that slew rate has an upper bound, that is a hardware constraint, but the optimal control method produces a gradient hardware waveform with a slew rate sometimes higher than this upper bound, for like 4%, which can sometimes cause a sequence failure. Besides, we find that the computation time of this method is actually longer than the length of the final gradient waveform. So assuming we have a sampling pattern that contains thousands of the different curves and requires several minutes to scan, we possibly need another several minutes to compute the gradient waveform using this method. In the time-sensitive scenario such as MRI, and especially for non-Cartesian MRI, which is known for its efficient acquisition, this several-minute pre-computation can entirely bury the acquisition efficiency introduced by non-Cartesian sampling. This limitations drives me to develop a more efficient method. We want this method to be general purpose, just like Lustig's, and simultaneously, we also want it to be faster. And even better, we want its computation time to be shorter than the gradient length, so that we can compute the gradient waveform while executing it, and also drop out the gradient pre-computation in the Lustig's method. Following, I will introduce the proposed method in details. The biggest challenge in the non-Cartesian gradient waveform design is how to control the slew rate amplitude, which is actually the second-order derivative of the K-space trajectory to time. For that, the optimal control method is a good example. So to control the slew rate amplitude, let's begin with a common observation in the Cartesian sampling. As shown in the upper part of this slide, Cartesian sampling is also known as uniform sampling because every adjacent samples have a constant interval in the k-space, and correspondingly, the gradient waveform has a constant amplitude. So to make the spheroid in non-Cartesian scenario have a constant amplitude, I propose to define a g-space whose axes are actually the amplitude of the gradient in different spatial axes. In such case, the problem to maintain a constant spheroid amplitude becomes a problem to plan a curve in the g-space with adjacent samples have a constant interval. Our method is built upon g-space and performs in a recursive manner, which means we calculate the next gradient vector by using the current one. This method is quite straightforward using the g-space representation, and we can see in this slide, the current gradient vector is represented by the black point in the left figure, and the right circle denotes the spheroid constraint. As we can see from the math definition of it, it actually defines a circle in the g-space. The gradient amplitude constraint also forms a circle, which is the big blue circle in this figure. Beyond these hardware constraints, we also want the gradient vector parallel to the current trajectory tangent. It might sound weird at the first glance. So let's take an example. If you are driving a car on some kind of trajectories, you must be supposed to make the car parallel to the path that you are driving on, or your car will likely to be off the path. So the same rule applies to the k-space sample. It also expected to have its velocity or gradient parallel to its current tangent, or your actual sampling position will likely be off the trajectory. Combining the constraints, we got the solution to the next gradient vector, as shown here. We can see that the constraints form a quadratic equation, and here is its root formula. It's a big step in our method, but the next problem is how to make sure the root of the quadratic actually exists. This problem can actually be solved in a kinetic way. We can think of a spaceship flying around the Earth. If it drives faster, it will move further from the Earth, and finally it will escape from its trajectory. The same rule applies to the k-space sample, where the gradient of the velocity of the k-space sample cannot be too fast, or more precisely, it cannot be faster than the escape velocity, which is a well-defined constraint in the kinetic science. Violating this constraint actually means the current available spheroid or acceleration will be no longer sufficient to hold the k-space sample on the trajectory. So for every recursive step, we simply limit the amplitude of the gradient vector below this constraint. This will necessarily ensure the existence of the quadratic root. However, there is still an edge case. Sometimes the escape velocity just drops so fast that our available spheroid is insufficient to even decelerate the k-space sample. Thus, the threshold itself would break the spheroid constraint. I paint the part of the gradient waveform violating the spheroid constraint red and otherwise green, as shown in the right figure. Please note that we can say as long as the gradient amplitude does not saturate the escape velocity, it's impossible to break the spheroid constraint. So we have to introduce a new strategy named discrete time forward and backward sweep. On a high level, we solve for the gradient waveform using the recursive method mentioned before, from the beginning of the trajectory to the end of the trajectory. And we solve again in an inverse direction. The final solution to the gradient amplitude is given by the minimum of the two gradient solutions. This strategy actually avoids using the escape velocity to throttle the gradient. Instead, it uses the gradient amplitude solved from another direction, which effectively avoids the spheroid violation. This is the main content of our proposed method. Next is the experiments we conducted to evaluate our method compared to Lustig's optimal control method. Here are the simulation experiments. We compared the generated gradient waveforms of the two methods in 7 different trajectories across 2D and 3D. Our method is on the right and the baseline is on the left. This slide is for 2D. And here is the 3D cases. We can see that we do not have the big slew rate spike that appears in the baseline method. Here is a benchmark between the two methods. We compared the two methods in terms of the computation time and the slew rate overshot, as shown in this table. The fewer steps consumed by our method basically leads to the substantial computational advancement by 1 order of magnitude. Our algorithm also reduces the slew rate overshot by 2 orders of magnitude. Actually, this improvement comes from the different discretization strategies of the two methods. As we can see from the previous slides, our method uses a time constant step, which means the output gradient waveform is naturally time parameterized. However, in the baseline method, which directly transplanted from the optimal control theory, has a constant arc length step, which is different from that of the gradient hardware. And to derive the time parameterized gradient waveform, an interpolation is needed. This basically leads to a drawback that the sampling pattern, the sampling density of the arc length domain must be much higher than that of the time domain to guarantee the interpolation accuracy. In contrast, our time uniform method is hardware intrinsic and does not need an interpolation. This difference basically leads to the orders of magnitude advancement in our method. Regarding the imaging quality of the time-optimal gradient waveform generated by our method, we also did some imaging experiments on both phantom and human knee. As we can see from the results, the non-Cartesian sampled images are clear and free of artifacts or distortions. We can also see that in the 2D imaging results, non-Cartesian sampled images have a significantly higher signal-to-noise ratio compared to the Cartesian reference. As a conclusion, our proposed method achieves 1 or 2 orders of magnitude improvements in terms of the computation speed and the slew rate accuracy. We achieve this by introducing a more efficient time uniform and hardware intrinsic sampling. For more details about this work, you can find our preprint on the archive. And if you are interested in the source code of our algorithm, I'd like to introduce my GitHub repository to you. You can also install our toolbox as a pip package, and in which I also implemented a trajectory library based on our method. This trajectory library is also used in our imaging experiments. So that's all about today's presentation. Thank you and hope you would enjoy with it.